Hello, good afternoon and good morning. I'd like to welcome you to the latest webinar from Restore America's Estuaries. My name is Hillary Stevens. I'm the Coastal Resilience Manager here. And I'd like to welcome you to our December 2020 webinar for the Living Shorelines Community of Practice. We're going to be hearing today from a professor at the University of Maryland about trade-off engineering, design, and biology for sustainable coastal infrastructure. Restore America's Estuaries, if you're not familiar with us, we are a national nonprofit based here in Washington, D.C., where at the moment it is snowing heavily, so I hope wherever you are safe and warm. We are an alliance organization for 10 member groups that you see on your map here. They're located around the country, and each of them is working in their local community to protect and restore their coastal resources. We serve as a convener and an advocate for them here in Washington, and really for anyone working in their coastal area around the country, and some of our efforts extend overseas as well. So I want to welcome you all. One quick update that I'm happy to pass along is it does look like there has been progress on the Living Shorelines Act of 2019, which was introduced to the Senate quite a while ago now, I think about 18 months ago, by Senator Kamala Harris and some others. And it looks like yesterday that it was voted out of committee. I'm trying to get more information. As you can imagine, Congress is a bit of a quagmire at the moment, but hope to have some more information to pass along for you should that actually be moving forward. That act directs NOAA to enact a grant program that would support living shorelines through state, municipal, and tribal governments. So we would all clearly like to see that happen. You are all attendees are in listen-only mode. So if you have any questions during the presentation today, please use the question box that's on the right side of your screen. You can feel free to enter them at any time during the presentation. We will save them until the end, and then I will read them out to our speaker, Professor Narden, at the end, and he'll be available to address those questions. We will be recording this webinar, and within a few days it'll be available on our YouTube channel. So that's, you can just go into YouTube and search for Restore America's Estuaries, and you'll find there the recording of this webinar as well as all of our previous ones. So if you ever want to take a look through our archive there's a lot of good stuff. So with that, I will go ahead and introduce our speaker. There we go. I'm having some issues getting the slides to advance, pardon me. Our speaker is William Narden. He is an assistant professor of environmental engineering at the Horn Point Lab of the University of Maryland Center for Environmental Science. His research goal is to understand the geomorphic mechanisms that control coastal environments and to predict the long-term trajectories. He earned his bachelor's and doctoral degrees at the University of Rome, and he is there currently with his family, so we are very appreciative of him accommodating the time zone change to be available to us from Italy. Before I pass over the microphone, I would also like to mention that Ray will be changing up our webinar format next year. We have several series of webinars in blue carbon, living shorelines, and some other topics. And we're going to be streamlining those next year. So look forward to more announcements after the new year about what that'll look like coming forward. So with that, I want to welcome William Narden, and I will pass the mic over to him.
Thank you, Hillary, and so much screen. So it looks good.
Yes, it looks good, and we can hear you. Thank you. Go right ahead.
Okay. So can you hear me very well? Yes.
Yes, your audio is coming through just fine.
Perfect. So I'm going to do this window too. So yes, I'm glad that I had this invitation from Hillary to present my work, and I think even if I'm in Italy now, I think it's important. I will show something from Italy too that is matching our work I'm doing in Maryland. But if you hear screaming, don't panic. It's just bedtime here, so it's 7 p.m. So anyway, thank you again for your invitation. And today I will take a look at the the living shoreline and nature-based solution with two different angles. Like, you know, because I'm an environmental engineer by my training, and by doing my PhD, I enlarged my interest on ecogeomorphology. So try to see not only the impact in the short term, but also looking at the projection in the long term of the landscape evolution, for example. And in this talk, I will try to show some of our experience that we are doing here in Maryland now, and trade-off among engineering design and biology for sustainable coastal infrastructure. I will talk about breakwaters and other infrastructure. Okay. Next slide. Okay, so this is just a short presentation outline. I will talk about oysters. So, and I will say that, I discovered oysters in On Point Laboratory at University of Maryland because I did postdocs around US a lot, Boston and Berkeley, California, but I never saw this passion for oysters. And then even if I'm a salt marsh guy working more on the marsh in SAV, I got interested in oysters too. So I think it's a really and On Point. It's a very and big environment where people is try really to share and involving other scientists in the science that they are performing. And I think oyster is really one of the big highway that for scientists in On Point that make science very interesting and at the top of the scientists, I think. So, but it's also very applied. The first part will be like in the oyster integration on grey infrastructure. The second part is more like on segment exchange between those bioreef and shoreline and marshes. So this is the brief introduction for the motivation. So there are many works so far. They are showing like how most of the human live near coast, and it's like more than 50% humans live within 200 kilometers of the coast. And if we look only to the US, large lands on coastal zones. So there's a dense human communities. There's 4 on 10 Americans that live just close by the coast. So it's really an important part, and not only for housing and communities, but also for economic. So the 6.6 trillion to US GDP is based along the coast of the US. And of course, because they are close by the coast so far, and depending also on the different part of the US, they are stressed by coastal evolution and also ocean evolution. So the sea level rise and the increasing storminess and create like a big threat for the community living along the coast. So coastal flooding due to extreme events and sea level rise is growing global concern. There is a huge amount of scientists working on this topic and try to understand, the best projection for those events. And the increasing coastal resiliency to these threats is a priority for many countries and a global need. So it's really something that we have to envision all together, because it's even like in some even if you look at the small estuaries, it's not like the action of someone on the other side of the estuary is not going to affect the other ones on the other side. So it's I say global, not only in the world, but also like in a global, in a world system, like an environmental system. So, and for example, like damages in the US from weather and climate events in 2005, 11 major events, in 2012, 4 major events, and the cost it's like 160 and 110 billion of dollars involved in those events. So it's a big damage, a big threat for the country. So, but if now I try to downscale it, be going to into Maryland, where I'm working, where I'm based, and where I'm mostly working, even if I'm doing work all around the world, but most of the work is based close by the On Point Laboratory. So, and sea level rise in the Chesapeake Bay is one of the greatest rates of sea level rise in the US, and is projected to rise to 1.12 meters by 2100. And recently, the nuisance flooding is something that is really increasingly affecting people. It's even like if you're not going to flood it directly in your house, but for example, like the roadways and other infrastructure, they're impacted, and they also affect your life, because if school bus cannot go on a flooded roadway, of course the students are not going to school. They stay home, and probably now with COVID-19 is not like a big problem because they stay home anyway. But most of them. But in the normal life, and those you can see here this graph at the bottom how this is increasing, and there are parts in Annapolis where those sunny day flooding are happening with the increasing the frequency. So, and to affect, if we think like only affected by the recent flooding, we are looking at a small portion of the problem, because there is also like other part of the problem, like the erosion along the coastlines, when where you have like wave action and marsh erosion or shoreline changes. So those breakwaters that I will show during my presentation, those are very common shoreline protection structure. I would say like everywhere in the world, but mostly when I read in Maryland, I saw like most of the coastlines is with riprap and breakwaters to protect along the along the coastline, the shoreline, the erosion, or try to control the erosion. But some of them are failing, and we are starting to map with the GIS all those structures they're failing, because we want to see if we can do something to make them at least a bit more dynamic. So this is just an example. So this is on the right side, you can see the eastern shore of Maryland. So those are typical like highlands and peninsula connected by one road. You can see here, for example, I want to show one of our study sites and one site that we discovered during our survey around the Chesapeake Bay. So, okay, so this is a roadway that's not serving many people, but serving like, and it's the only way they can access a small portion of this peninsula. And but there are like several families living on this area, and they're connected with just one road. And this road, it's protected by breakwaters. They are drowning, even because you can see also the signs of erosion along here, the coastlines, how those marshes are almost here completely vanished, here still eroding, and you can see like this shape called like geomorphologically gully. This shows like the signs of erosion along the shoreline. And so there are multiple of this situation around. If you go like on the eastern shore, we have like students going on the Google map and mapping all those infrastructure failing, or not failing now, but probably in the near future. Or here another example of the riprap just southern than their area. You can see here a riprap formation all along the coastline here, and you can see all those signs of erosion here. So it's a picture by Google Earth, or Google Earth uses like a Landsat images, so you can go backward of 30 years, and we are mapping those. These are a good image. You can see very high resolution, and we are mapping those situations here. And you can see now in 2016. So this is like a node which also check the tides. There's no major wave event. This is just, it's a failing event. And you can see here a failing part here, where also if you go down here, it just was already failing in 1998. This area, it's because it's subject to very high wave action, and also probably subsidence and other effects, sea level rise, are affecting those coastlines. So this is just an example. So the big question here, so there are, during my presentation, there will be like multiple questions. One of the first question I'm asking here myself when I start to work on these infrastructures, do we keep use this approach, or we want to change and see if we can make those structure valuable and more dynamic? So, and I think I discovered the living shoreline when I arrived here in Maryland. So I really, so there are multiple names. in Europe, if you go in the Netherlands, is a natural-based solution, or green engineering, or natural-based engineering. So, but in Maryland, it was like a living shoreline. So, and then I saw like, okay, this is something I have to study for sure, because it's something really attractive and really, I think I'm envisioning the future here, how, you know, making design with those kind of living infrastructure, I would say. So probably, you know, one major study from Timmerman et al. Showed, I didn't have this slide here, but I want to say something because, you know, probably living shoreline can be adapted in some certain condition, like even, you know, can be probably like not use even like a natural-based solution on the open ocean, because, you know, the energy of the waves, of course, are different. But I think for Chesapeake Bay and coastal bays, I think it's a very suitable situation, and this should be like a evolved, try to understand how the best way, the best practice to adopt this new technology. So, of course, as all the technology, and I'm an engineer, so I'm always have like a different choices, right? If I can go gray and have all my past statistical adaptation of this infrastructure to the coastlines. For green infrastructure, we are developing now, and we are like, oh, there are some decades of experience, so we can use those data to understand the best situation to adapt them. So there are pros and cons. So pros are like, of course, because it's natural, we are going to enhance the habitat. So adding habitat for other species, of course, we're going to introduce more living plants and other crabs or fish, then is enhancing the quality of the habitat, and is also able to self-recovery after small storms, because if you think like some structure that is failing, you have to go there and add the blocks or add the rocks where the structure was failing. But this is just this structure, probably you can help, like this living structure, you can help them to readapt along the coastlines. And they can keep pace with sea level rise, and those are like even cheaper because we don't need to move like big materials or heavy materials like rocks. But there are also cons, right? So the maturity of the protection and recovery can take a long time, because it's not, probably we can understand how to boost probably those reaction after storms, and the protection is variable and the outcomes can be uncertain, because of course we don't have background on those infrastructure, and permitting can be more difficult because right now we are implementing. So, but I'm not thinking about the living shoreline, because the living shoreline it's well established in Maryland. But if we want to do some variation of the living shoreline, this I'm thinking something like that, or there are limited expertise. So still like if we compare to the gray infrastructure. So, and so here, a first question, another question I'm asking is, how can Oyster be used for hybrid infrastructure? How we can implement them inside the hybrid infrastructure? We know that Oysters has been like an attractive trace of reefs for retrofit infrastructure, and Oyster can create ecologically valuable habitat because it's still like a living features that we're going to have. They can keep pace with sea level rise, so they're going to create a sea level rise rates, because once they are flooded, if you ask, if they live in some subtidal area, if the water increase, they can probably keep pace and grow more higher. So they also, because they are as a living features, they are not like smooth. They create their roughness. So this roughness is a good also process to improve the wave dampening. And reefs self-repair. So once they get some damage, they are able to oysters to rebuild with the new spats on different parts. So this is just a modeling effort, because I'm also doing a lot of modeling and so modeling, numerical modeling, and field work. I will show both of them. And but this, I think, is something that this article was really important by Brandon in 2016, and is showing like the impact of historic reefs, how they can dampen modern hurricane waves. And these are based on New York Harbor, and if I remember, yeah, I think New York Harbor, and they try to add like the Hurricane Sandy forcing of the wave and wind, and so if you look at the first, sorry, on the right, on the top, where is the control. So this is like the situation without Oyster Reef, because historically there in front of those coastlines there was like a very long line of oyster reefs, and then if we restore the oyster reef here, we do like the same modeling exercise, you can see that the waves are dampened more than half meter in some situations. So you can see the variation here, the change between half meter to 1.5 meter along the coastlines. Those blue here is showing the dampening of those waves. So yeah, so this is one exercise that it will inspire me to do another with not like a sandy, but with a different kind of storm condition in a different place like Chesapeake Bay. So when reef construct, so they construct like they build, if you do like a sea level rise projection, the level is increasing, so they start to reach top and try to increase the height of the reef. And then of course they, during some growth condition, they can reach and the top of the water level and also dampen waves, depending on on the tides and the different ecological constraints too. So yeah, so the biological constraints, those of course, those are live, those are animals, so they are suffering. As I'm an engineer. I'm sorry if I offend some ecologists, because those part is really from this project, a multidisciplinary project with other biologists. It's me and biochemistry people. Like I will show them at the end. But I'm trying to. I want to include this part because I think it's really important. And for me, as an engineer, when I envisioned this problem, I understood a lot of designs problem that I was facing. So of course, like those are two different parts of this oyster reef. You can see the water going up and down. So there are optimal conditions for the oysters to grow. And the high subtidal, especially the high subtidal, they are suffering for different stressors. They can from the weather, but can be also from human impact. And so growth is very great in the survival. Also is great in the subtidal area because they are always flooded, but they can also get out, and looks like that when they get out, they can accrete better than shells. So what's the hazards? Here there are some picture of the Chesapeake Bay, wintertime, caused by beverage, and you can see like how those ice sheets moving around, for example, and those all ice forming on top of the water, because here also like there's a huge gradient of salinity along the Chesapeake Bay. So the upper part presents a lot of fresh water, is also prone to create more ice and get more, so getting worse condition for the oyster reef growth. So, and this just showing so the hazard of living in a high intertidal, so ice dislodge oysters and freeze animals, killing them, and of course reducing the them effect in the during storms. So, but also like in summertime when the living again in the high intertidal, so the air exposure create a desiccation stress on those oysters, and they're gonna die too. So, and there's also like some human impact by the easy harvesting where they are exposed. So in the high intertidal. So, essentially the lesson we learn from the biology is we don't want to stay too high, because too high can be dangerous. But as an engineer, again, I'm sorry if I'm repeating every time, because this is I think really the real topic of this talk, is try to see how even living shoreline or any natural-based solution has to be multidisciplinary. It's not like only engineering, there's also ecologists and biogeochemistry and geologists. It's all together try to understand the best way to design those infrastructure. So as an engineer, these are very, very basic image that you have on all your book when you start to do some design of breakwaters. So we engineers are interested in B, here, how long is this breakwater, and the AC, how high is this breakwater? Because we want to dampen all the waves. We don't want any waves going behind the breakwater. We want the maximum impact on the breakwater, and also roughness. Here is not, I think, a parameter here, but it's also roughness is here on the top, making more dissipation of waves. So if I try to summarize this concept, it's just a graph showing like some certain trend. So the percentage of wave dampening depends on the structure height. So, but it's something that is not ecologically convenient, because ecologically, as I showed before, being very high can be a problem for the animals to die. So this is just this is a little Choptank River. I want to show just some sign of erosion that we are facing in the last. This is a Google Earth engine and showing like images of those small islands in front of the little Choptank River mouth, and you can see like the signs of erosion that we are facing. And this is just behind in our backyard of On Point, because we are on the Choptank River. This is just southern than us. And those like the yellow part here is showing the extension of the islands 2016, and the red part is showing the extension of those islands in 1984, right? Yes, 84, yeah. So, and also here is like the coastline is changing too. So, so if you want to save those lands, we have to install structure that are able to dampen the waves. And so to dampen the waves, for example, with the green infrastructure, we have to understand how to retrofit with the Oyster the infrastructure, because if we deploy those infrastructure as a green infrastructure, they are not able to be facing changes along the time. So live plants and the oyster probably can readapt along the time. So those are like some example of common tactics for oyster shoreline protection. Loose shell is not used anymore. So shell beds are used, but I think oyster castle, the one we use in our projects, you can see here deployed. They are kind of Lego, and they interlock together, and they can be forming a different features. Depending on where you're going to deploy, they can dampen waves and be a home for oysters larvae to start to build oyster reef. So before starting our experiment, we did some modeling design. So here we use like a depth 3D model coupled with SWAN. Those models, SWAN is a wave generator model, and depth 3D is a hydromorphodynamic model. So it's looking at the hydrodynamics, but also moving the sediment transport can create different landscape evolutions. So here the exercise you can see, so this is like just the domain. You can see here very small our breakwater, and so the waves are coming from east to west, and we envision like two different slopes because our study sites have different slopes, and we envision different distance of these breakwaters from the marsh. But again, because I'm also like marsh guy, I want to see the impact of marsh in the long term. I'm not just saying, okay, I want to dampen the wave, I want to save the marsh boundary, but the marsh boundary, it's something that also is a source of sediment also for the marsh platform. You know, I want to see the impact of those infrastructure on the marsh. So when doing our modeling exercise, we take account the length of the breakwater, block configuration, orientation, and the impact on surrounding ecology, even on SAV. So I will not show you nothing here because we are still working in progress. But SAV is something that is also affected by those infrastructure. So, the big question is like, again, like how do we install and optimize our existing infrastructure? So here, we'll start this video here. So this is like our breakwater. Waves are coming from this part here. This is just the model. Here is like the marsh platform. This orange part is the higher part. And you can see here during a few storm events, depending on the tide, how the sediment it's piled up along the shoreline here. Right? You can see like the difference between this area and the area behind the breakwater, because of course the breakwaters, it's also like these are very well known. The breakwater make a lot of deposition on the back because they dampen waves, so the waves are not able to resuspend sediment on the back of the breakwater because they cannot pass the breakwater. And here on the right, you can see another plot showing so along these blue dashed lines and the red dashed lines here, those two different lines. So the blue line is showing like behind and along the, you know, on top of the breakwater. You can see how the sediment is displaced here. So this is the marsh boundary, just here. So it's, of course, the marsh creates a higher roughness, and all the sediment reward by the waves is deposited right at the boundary of the marsh. So with the breakwater, of course, again, we save the boundary of the marsh. But with the red line here, showing the part of the domain very far away from the breakwater, is showing that the effect is not bad. Even if we erode some part of the boundary of the marsh, we are able to winnow this sediment inside the marsh. So it's a good, you know, good feedback anyway. So because we make it more resilient this platform of marsh, so we are able to send sediment on top. But if we had oysters, of course, we add another layer of dampening, and we have a even higher sediment depositing on the back of the breakwater. So in some way, we can say like it's good because we are able to pile up more sediment on behind. We're going to save more sediment behind the breakwater, but we are not able to send this sediment. Is vital for marsh to create and survive the sea level rise. Okay, so this was like more the modeling effort that we conduct with my students, and here I start the project we are conducting at HPL. In the left image, you can see the Choptank River. Here in the red box, highlighted is the HPL campus. This is HPL. Inside our campus, we have this Lake Cove. It's called Lake Cove. It's a cove, and on this cove we are stuck because just inside our campus we can walk there 5 minutes walking, and it's amazing because it's full of deer and animals. It's great old forest, but this forest is suffering. So you can see the signs of erosion. So since I arrived in HPL 2017, I saw like a dozen of trees falling down with storms, with erosion. So, and this experiment is based in 2 different geological parts. These are cliffs with a forest on the back with the very mature trees. And here in the upper part, where is my pointer here, there's like a pocket marsh where is mostly Phragmites, and we have like also SAV beds in front of this area here. So then, especially winter time and during storms, you can see signs of very clear signs of erosion. We deployed our experiment here, and the first year we asked for the permit, and there was this is the reason why also I'm talking about like they can be hard at the beginning. I say it can be hard to ask for a permit because when we did our permit paperwork, there was nothing mentioning like it was a living shoreline, but it's not living shoreline. These are oysters, kind of a bioreef, but there was nothing. We have to sign other and start to describe our work and see and envision how this can be progressed. It was like it's not like a gray infrastructure, it's a green infrastructure, but right now it's gray. So in the near future will be green. So and you can see like the different water level here. So those are the 4 breakwaters we built. And yeah, okay, I will describe later like the breakwater, but I want to say something about UMCES and Oysters again. Give some numbers because UMCES is a home of largest oyster hatchery in North America, and from 500 million to more than 1 billion spats on shell produced annually, depending on the salinity they have outside the hatchery, and these are on the eastern shore and other parts of the Chesapeake Bay. We are one of the biggest oyster restoration in the history, like 5 sub-estuaries with a restoration of more than $51 million invested, and also 3.12 square kilometer of restoration area and 3.69 billion of oysters planted. So this was like this was right to mention because we have to understand the context of UMCES and On Point, and we are lucky to have this hatchery. They really supported us, will help us to be successful in our experiments. So, and this is one of the images of our first blocks that we deployed in 2018. So you can see here we seeded those blocks in a tank in the hatchery, and then before, because we didn't get our permit, we deployed like close by the coastline and see how the salinity was like more an ecological experiment because we're waiting for the permit. But then you can see here how the oysters changed from 10 cents, 20 cents size to few centimeters, and this is like 2020. This is summertime. So yeah, those are like our we use two different way to seed the blocks. One in the tank, and that one was really successful. But also this one was successful too. We did like in the field because it was easier for us, even if we want to reseed again the blocks and see how how many times you have to seed to be successful for the larvae to start to grow. So the yeah, and then we did in our experiment we did a Bachy control. So we first we did like the one we seeded the first one, and the second we didn't seed because we want to see also recruitment from the neighboring breakwaters if it's able to colonize and send oyster spat to those other one. And those first two are essentially breaking waves. You can see waves are very prominent from north, and it is up like especially in fall season. And those are protecting the shoreline here. There's mostly like a marsh, and 3 and 4 are protecting this cliff and forested area. So of course, once we deployed the experiment, we after 1 year we start to monitor different aspects of this structure. On the left plot here, you can see for the yellow line here showing like again our breakwaters, and depending on the color of those lines those are the transects we are monitoring with the GPS high resolution. We have like a station in our campus from NOAA, and also we have our RTK, and we measure along those lines here the accretion and erosion. So you can see that in front mostly is eroding because it's an impact. So it is eroding if we check also with the original bathymetry, it's a very shallow water environment, but the reflection of the waves and the refraction from like the structure, of course, is making eroding in front of the structure. But it's like a few centimeters, like probably not too much. Also, we had like a few centimeters of deposition on the back. If we look here, the transect 4 is one of the most representative situation. And but it's also like interesting to note that the structure is sinking. This is something that we are facing at the beginning. We didn't take care too much, but then we found there was like even another effect is essentially the weight on the soft mud. It's even if we use like at the bottom a fence, a metallic fence with other to stabilize the structure, is anyway sinking a little bit because it's it's very soft mud. And it, again, it's like a few centimeters, but something we are investigating to now and try to understand. It's also like rotating a little bit. So and the red one, the red line is from November 2019, and the blue line is from June 2020 here. So, and we also like, so that the erosion here on the marsh boundary is stopped, so it's not progressing anymore. But the cliff is still collapsing because we discovered there's also like something from hydrogeological, so the water goes inside the cliff and really melt the sediment down, and it's also maybe collapsing. But anyway, the sediment is not loose; it's just building behind the breakwater. So it's those are 10 meters long breakwater, and the distance between them is 10 meters to allow the sediment to flush in and out of the system. So okay, so this part is on the experiment we did on in Chesapeake Bay, but also we are conducting another experiment here in Italy on the Po Delta in the northern part of Italy. I will dedicate like a few minutes about this work because also is looking at dispersion of oyster larvae. This is something we want to do in Chesapeake Bay too. So this bay here is called like Goro Bay, and Goro Bay produces like a 50%, or no, sorry, 60% of the clam economy, clams economy, and for Italy. And there's also like producing 30, I think between 30 to 35% of the entire production of Europe. It's a very huge economy there. So and when we talk with those fishermen, they say like, well, we have two problems. One, it's we can see like some changes in the wave action, and also we have this problem with the clams that we're sending with the, when they select the clams, some part of the clams goes to the landfill. So say we want to use those lands. So and we envision like a project on with for because this is also like involving blue carbon. Say okay, we want to take those oysters. So these clams that are originally from those bay, we want to use them and build something with them. So we so like the oyster blocks that I showed, like the oyster castle are made essentially as cinder blocks, and there are cement and some fragment of oyster shell. Those blocks are entirely formed of clam shell. So they grain them, they fix them in a very high temperature oven, and then they assemble them with a 2D printer that they are developing for 3D printing like cement. We asked them to do this kind of structure, and it's a project in collaboration with the University of Ferrara, and I got involved as a modeler and also as a co-PI for this project. And as you can see, we decided to do like some fancy shape to create more habitat also for fish and to increase the habitat. So this deposition on the delta, those are like just the grid for the model. And here is the experiment we did for understanding the larvae movement along the coastline. And there are two prevalent winds, one from north, so dispersing more the oyster larvae down. And also, so I'm still saying oyster larvae because I would say later why. So, and then this black dot shows like the release point of our larvae. And then when you have a south, is more like taking northern and constricting close by the bay the larvae. So I saw oyster larvae because the northern part of the Adriatic Sea in Italy was historically a big producer of oysters. But then they got a disease and they lost most of the population. They are trying to reintroduce now oysters. They have these golden oysters. Those are kind of yellowish outside. And they, on this bioreef, they also touched with some way, I don't know, like more ecologists did this work with some natural glue, I would say, on the all around the reef, and then they seeded them. So they want to see if oysters are able to go back, and they want to see. But you know, the big concern about the clam industry say, okay, but do not go in our field because we don't want oysters here. We want clams. So and then we did this study, and you know, this is the reason why we went just outside the lagoon because we want to. We don't want to disperse inside the lagoon. Even you know they are ready to be getting some of them inside the lagoon, but mostly they will be outside the lagoon. So those like another image with a more wind direction and the direction of the currents along the and this just it's me like so we did like a presentation of this reef, and it's just to show how big is the reef. Is like 1 meter, is like essentially like a 1 cubic meter. And we did also like other experiment looking at with a float energy, another model with more fluid dynamics model, see if what's the impact of waves, because we don't want this structure to capsize or you know wash it away. And we did some also structural calculation to see if this you know if we have to if the place we choose where for the deployment was good or not. And so this is some of our experiment that we did for you know for the minute waves. We saw like you know also the action of the force on these blocks, and also the shear stress to see even if we had like some extra force. But it looks like the you know should be there if you know if not a major storm is coming, because it's again is at the mouth of the lagoon, is a very shallow water environment, and probably the waves can increase the action along a lot during the time. So then, and then this drives to another experiment, another project we are doing in South Italy now with a bigger. So this is more like for restoration project. So we build another different blocks, but you know the 3D printer can do like a 1.5 meter as a dimension, height and length. So we adapted we connected those 4 blocks together, and we're going to deploy mostly in this region, mostly for habitat, because it's can be house for fishery. It is more like fishery habitat, and we implemented some part to save in case like you know there was like a fisherman with a drag digging up the structures. So yeah, so this all, and concluding, I want to say that you know oysters we are doing, and they can be directly integrated with green infrastructure, and even like in the green part of the living shoreline. Integration must consider a balance between biology, species specific, and engineering constraints, structure specific. So it's not only one way thinking. We have to think multidisciplinary. And the oyster reef impacts sediment delivery to the shoreline and marshes can be good for the marsh boundary, but for the sediment supply to the marsh platform, we are still trying to understand to quantify consistently and understand if can be good or not, because in the long term probably can be a problem. So the marsh are a dynamic system, so they readapt. So if the shoreline is the boundary of the marsh is eroding, it's all sorts of sediment for the platform. So, and I want to just acknowledge some of my collaborators here, Jeff Cohen for the biochemistry part, because also we are seeing the effect on the nutrients of those blocks, and Jeff is working very hard on this part, and Jacobo is one of my students working on the more on the modeling part and the field part, and Matt, it's really the other part of me and Matt start this project together, thinking, okay, we have to. He's an ecologist, he's an ecophysiologist, he's also an oyster aquaculture expert. So we have to think together a way to do like oyster restoration the right way. Thank you.
Thank you so much. That was absolutely fascinating, and I am so glad that you took a few moments to talk about what you are working on there in Italy as well. I was going to ask about that. So to those of you on the line, we do have time for just a couple of questions, so feel free to type those into the question box and I will take them as they come. Right now we have a question from Bhaskar. He asks, how many Living Shorelines project in Maryland have oyster reef as a component, and how well have they performed?
Well, so far, I think probably he knows better than me, because I'm not. I think this is the only one that we are working on now, but I'm not sure how many there are in Maryland so far. So I know there are different projects. We are proposing projects. We are trying to implement as much as possible, because we know that it can be something that should be implemented. And you know, I guess I will say that I don't know the numbers, but for sure our project is one project that is working on this and try. We are starting with just the breakwaters, but we get funded now from NIFWIF. So those are like at the bottom, you can see our Dominion Energy donates money for build the blocks, and Palmer Foundation also helped with to buy the blocks and seed the blocks, and also National Wildlife Federation helped a lot, is a partner with us, and we have now a project going on Bill Barton Pier. We want to start. We have more to deploy in the Lake Cove. We started with just the 4 breakwaters, but we are allowed to do other works by Maryland Department of Environment. We are implementing now one of the dilapidated it's a breakwater dilapidated. It's in front of the Cove, and we want to implement there other blocks. And we are working with Palmer Foundation to another fund to implement. I think it's a new technology, and so it's very well known in the estuary restoration. So in Virginia, is very well known. I saw in Virginia Coast Reserve in on the eastern shore of Virginia, I saw their projects working and also quantifying the effects of wet dampening. There are other works, but in Maryland, I think we have tried to now implement and try to push this direction as much as possible.
That's great. Bhaskar says that he would love to get in touch with you when you get back, so I'll make sure you guys know how to reach each other. Okay. From Maryland, she says, I love hearing about the Italian projects and baking your own clamshell cement. Can you share plans and specs for the mix and for the reef structures made for them?
Oh, so say again, I lost the last part of the question.
Oh, sure. She was just fascinated by the works that you're doing in Italy and how you're making your own clamshell cement, and wants to know if you can share the plans and the recipe for making it and what you intend to be working on there.
Well, so this is a company, it's a startup working on it, and it has a patent on the cement, so I cannot share nothing because I have no idea how they do that. Well, I know the procedure because we present together last fall, and I presented more the engineering part, and but they didn't show too much about this, you know, the mixture they're using. Just what I know, it's this 3D printing is firstly printing in a different density, and then you know, it's kind of making sculpture inside a cubic meter, and then they remove the external part is more soft, and then and then it's coming out the reef. It's not like so they work on density of those cements. The external part of the cement is very soft. The concrete part, sorry, the part in with the bioreef is very hard. So and then it's coming out the soft part around, and then the shape is coming out this way. Actually, at the end they have the water on top, and then is all the external part is melting down in the water.
Wow, fascinating. Well, we'll be very curious to hear more about that as those kind of things become more common. I want to keep an eye on the time. We have just a couple of minutes here to the top of the hour. So I think we will wrap it up there. I want to thank you so much for making time. I understand it is bedtime there, and you might have young children that would love a kiss from daddy before they go to bed. So I want to thank you again. I will connect you with Bhaskar, and I do look forward to whenever you make your way back to the US to talk with you further. So thank you again. And to everyone else, as I said, please look forward to notifications in the new year about the continuation of the Ray webinar series. Thanks again. Take care, happy holidays, and best of luck in the new year for everyone.
Bye, thank you.